Okay, so the way that this experiment works, right, is that you have, and it's an interferometer, so you have a beam splitter, you have two different light paths, and so the light initially comes in from the left, the beam gets split, so half the light goes in arm B, half the light goes in arm A. When they get recombined by the beam splitter and measured by the detector, those two waves will interfere constructively or destructively depending on the angle that you measure on the detector, and that will create an interference pattern in space that varies basically according to the wavelength of light and the geometric details. Okay. Now, if the total travel time of the two light waves in A and B are the same, then that interference pattern, those interference fringes will be centered in the detector, or can be made to be so by the experimentalist just by calibrating the instrument. But if the total travel time of the light waves in these two arms are different, then that interference pattern, the interference fringes, will shift left or right. Okay, so that's how they propose to measure the speed of the Earth through the ether. Is that they expected those two times to be different because they expected the velocities to be different in these different arms, which would lead to different times and a shift in the interference pattern. Now, to start to analyze this experiment, I should say that you're going to be analyzing this in a little bit more detail in class, and we'll do that together. But what we're going to do now is just sort of make a simple analysis. We're going to try to determine what Michelson and Morley should have seen in terms of how much shifting of the fringes given their geometry and the speed of the Earth around the Sun, 30 kilometers per second, and then we're going to compare that with what they did measure. So the first thing that we do is that if we have to define the speed of light that they would measure if the Earth were stationary with respect to the ether, and we'll define that as c. So this is what we typically use in physics to define the speed of light, and so we'll define that as c, and that's again the speed of light that would be measured if the Earth were at rest with respect to the ether. Okay, so it's in the rest frame of the ether. Now, but they didn't expect that, right? They expected the Earth to be moving with respect to the ether, and so an observer on Earth would measure a different velocity. C, we'll call that c sub e, c sub Earth, for the light as it moves, as the Earth moves through the ether, and the Earth we're going to define that velocity of the Earth through the ether as v sub e, v sub Earth. So if the Earth-bound observer was measuring the speed of light in a direction which was parallel to the Earth's velocity, okay, through the ether, then that observer should measure a speed equal to the speed of light in the rest frame of the ether minus the velocity of the Earth through the ether. So basically, the Earth is chasing the light, and so it would measure a smaller speed by that factor. Similarly, if the observer was measuring in a direction anti-parallel to the Earth's velocity through the ether, then they would measure the sum of the speed of light in the rest frame of the ether plus the velocity of the Earth through the ether. And finally, if they're measuring in a perpendicular direction, that is perpendicular to the direction of the Earth's motion through the ether, then they would measure this, and again, this is something which we'll go over a little bit more in class. Okay, so they'd measure this quantity.